It is with great honor that I may now introduce you to my colleague, Bram Volbeda, our AI for Health teammate.
Thank you, Cecilia, for the introduction. And I'm going to tell you a little bit about how FruitPunch AI is applying its AI for Health vision. And then we have two presentations from both the AI for Health projects, so that's really exciting. First, what is AI for Health to us? Because there are more organizations that do so, but what does FruitPunch AI mean when we talk about AI for Health? So it's our mission to apply AI for good, but in this case, specifically for the healthcare sector. And as Cecilia mentioned, at FruitPunch AI, we are all about applying AI for good. And that comes down to solving the challenges from the Sustainable Development Goals. So what we want to do is work together with as much organizations as possible to reach the third Sustainable Development Goal, good health and well-being for all. That is our vision and our goal. So how are we going to approach this? We want to teach AI engineers a problem-first mindset with challenging projects from the clinic. So not a predefined project from the university, from a certain course where like 20 people are working on the same assignment. No, these are challenges that we put together with hospitals on a national scale. And we have teams that are trying to solve these challenges and applying their knowledge for good. And in the meanwhile, we as FruitPunch AI are expanding our network within the healthcare sector to speed up the implementation of AI. So why now AI for Health? It has been tried before, but I believe, and many others do, that the unprecedented increase in computing power has enabled us to more accessible machine learning and AI concepts and to apply those concepts in the healthcare sector. And of course, to even start working or developing machine learning algorithms, we need data, and introducing the electronic health records has been a major factor in contributing, making these kinds of projects possible. And then some toughness to crack. Those are some points we have experienced as FruitPunch AI, but I believe there are lots of experts today that are going to tell and know way more about this. But from FruitPunch AI perspective, these are some challenges that we really have to face when applying AI in the healthcare sector. And that is the confidentiality and privacy issues. It's very sensitive data, privacy sensitive data that we're working with. So we need a framework in which we can securely and safely share this data with each other. And that sometimes proves to be a problem. And most proposed solutions to challenges must be so-called explainable AI in order to be accepted by physicians and also make an impact. We can't just have an algorithm deciding or supporting a physician in their decision making, but not explain why the AI thinks what it thinks. So those are some additional challenges we have when these projects are working on their case. And I'm now going to tell you the two challenges that we currently have, and then team members from both teams will take over and share their results, but also the case. So the first challenge that we started a couple of months ago was with the MUMC in Maastricht. And that was the development of an AI-based tool for automatic segmentation of the lungs from thoracic X-ray images using a General Adversarial Network, so a GAN, to generalize to a wide variety of patients. And the second challenge is started quite recently together with the ETZ in Tilburg. And that's the development, the critical evaluation and implementation of a hospital-wide tool that outperforms the current golden standard when it comes to early warning systems. So these are the challenges that we currently have. And I would now like to invite Dorian. He is a team member of the first project to take over and share his presentation with us.
All right, thank you, Bram and Cecilia, for the wonderful introduction. I'm gonna share my screen now. So I hope everything is visible.
Yes.
All right. So my name is Dorian. I am a team member of the AI for Health team that started in February, and we are trying to make a generative adversarial model to segment X-ray images of the lungs. And I'm first going to give you a quick introduction of who we are. We have Jari, myself, Meert van den Berg, Jans, and Meerte Kater, and we're a multidisciplinary team. Some of us are data scientists, some are magical engineers, and we have one AI specialist. And then, of course, we have Bram, our team supervisor, who supported us on every aspect along the way. And we have our client from Mastro, Jennifer Dant, who also helped us when we faced some difficult roadblocks or inspired us in different ways in to get to multiple solutions. All right, so what are we talking about when we are talking about segmentation? I've given you a plain example. So first we get a normal X-ray image. This is a thorax X-ray from the lungs. Then normally a radiologist has to draw a mask over it, and then this can be used for the classification or to determine if there are certain lung infections or certain diseases present. And nowadays, because of the COVID-19 virus, a lot of hospitals use this as a first step when admitting patients to the hospital, because taking X-ray pictures is a quite easy and very quick way to determine if a person is infected with COVID. But the only problem is that Cecilia already mentioned it is a very repetitive task and a very time-consuming task. And the time from radiologists could be used in a way more efficient way than by drawing these masks themselves. And that's why we wanted to create a model that would do it for them. And also, because the determination of the disease is one of the reasons why we're doing this, but also if you want to train a model to classify COVID-19, it is better to train the model on only the lungs instead of the whole picture, because as you can see right here, every picture has all other kinds of types of noise or in the left picture you can see, I think it's a pacemaker or something, and this could a model can recognize this and maybe misclassify something as COVID or not. You might already have seen some COVID classification models last year. A lot of researchers looked into this very deeply and were very eager to produce their best COVID classification models. As you can see, some reported very high specificities, but also accuracies of 100% were recorded. And there have to be some red flags if you see accuracies of this high. And these red flags were validated by the next paper that came along in March. This was 1 month after we started our project, so it was very nice for us to see that we were on the right path. So this paper was called Common Pitfalls and Recommendations for Using Machine Learning to Detect and Prognosticate for COVID-19. And they reviewed over 2,000 studies that were published in 2020. And they reviewed all of them, and they found that none of the models that were proposed in these papers were able to clearly identify and to be of any potential clinical use because of methodological flaws and underlying biases. And one of these underlying biases, as I already mentioned, is that a lot of these images have some kind of annotation within the image. So as you can see here, there's an arrow or an L, or there's a portable, and these kind of annotations can vary a lot between data sets. So if one of the data sets is, for example, only from COVID-19 positive patients and they all have the same little L in the corner, then a model we train on it can recognize that, oh, it has an L, so it's probably COVID positive. And that's not what we want to train our model on. We want to train our model on what is inside the lungs, so we can create a robust model. So how are we going to do this? Well, we're doing it with a generative adversarial network, and this is a little bit how it works. We got two models, and it starts off with an input image. So let's say a normal image of a thorax X-ray. Then it goes into the generator model, and it generates a example or a mask, a generated mask. Then this generated mask is fed into a discriminator model together with the real mask that was drawn by a radiologist. Then the discriminator model will decide which one is fake or real, and by classifying the fake or real, it creates a loss function that is used to update the generator model again. So, for example, we can see here that this generated example still does not really 100% confirm to the real example. These not overlapping pixels will be added up, and with the mean squared error will be given back to the generator model to improve their weights and create better generated examples. This results in some kind of zero-sum game, because you can imagine how much better the generator is going to do, how much harder it gets for the discriminator to be able to classify real or fake. So the models are trained separately, and for every step the generator gets better, the discriminator gets a little bit worse. So on the next step, the discriminator is trained again, so it can get a little bit better, so our generator can get a little bit better. And in that way, you can see right here, these are the loss values along the way, and I've also added the mean loss values from a couple of steps because it's more clear that you can see that it's actually going down. But the reason why it's going up and down is just because the generator and the discriminator are in this kind of game, and they're battling each other to get as good results as possible. So these are kind of the results that we generated. This was around like after 50 epochs. It was, I think, 2.5 hours of training. You can see that not all of them are completely perfect, but generally is doing very nice, very good work. And yeah, we actually are thinking of writing a scientific paper about it, because we think that the results are coming out very good. So what is the next step? It's up to Mastro. As you can see, I already explained this a little bit. The current workflow now has a lot of time-consuming activity by radiologists, and we want to replace that with an AI. So we want just the AI to be able to classify COVID or other types of lung infectious diseases. So that this will improve the workflow in the hospitals, and we can use AI to improve our healthcare system and to improve our well-being. All right, so that is what we are doing at FruitPunch. If there are any questions, please put them in the chat so I can see them. And I believe there is a little bit of a delay, so I would just share some of my experience from FruitPunch AI. Well, up to last Friday, I hadn't met my teammates in real life, but here you can see 3 of them. Fortunately, Jan's camera wasn't working this day, but we learned a lot, especially for programming, from the whole programming of this project, but also in working together for a client. And yeah, the whole experience was very good to me. All right, I see a question. How did we identify the optimal number of epochs? So we used the dice loss function. And what the dice loss function does is it takes the generated example and the real example, and it calculates how many pixels are overlapping. So when there are when 99% of the pixels overlap, this is a very good generated example, and we use that 99% then as like as a loss function. So when it doesn't go higher than the 99%, after 5 epochs, it stops. So it's a bit of early stopping technique.
All right. Thank you, Dorian, for this presentation.